This video will cover the second part of the acids topic and will include buffers, titration curves and salt hydrolysis. Before we start, just a reminder of the acid definitions that can be found in your SEA glossary. Buffers are solutions which resist the changes in pH on addition of small amounts of acid or alkali. We can get two types of buffers. We have acidic buffers, which are the more common buffer that we're going to look at in this topic, which are made from a weak acid and its sodium or potassium salt. We can meet alkaline buffers, which are made from a weak base, for example ammonia, and its salt, ammonium chloride. Buffers can be found in biological systems such as the saliva, the stomach and blood, where it is essential that the pH stays constant. Most enzymes work best at particular pH values. Buffers may also be found in household and cosmetic products which need to control their pH values. What is a buffer? A buffer is a weak acid and the salt of a weak acid, the conjugate base. A weak acid only partially dissociates, so we will have mostly the weak acid in the solution. However, if we dissolve up a salt of the weak acid, for example sodium ethanoate, we will now have a large reservoir of ethanoate ions. So when we take a weak acid and the salt of the weak acid together, we have a large reservoir of the weak acid, which is undissociated, and we also have a large reservoir of the conjugate base. How does a buffer work? First of all, write the two equations that we have already met. When we add H plus ions, the H plus ions react with the ethanoate ions which have been produced by the conjugate base, and this pushes the position of equilibrium to move to the left and the H plus ions have been removed. This keeps the pH almost constant. What happens when we add OH minus ions? In this case, the OH minus ions react with the undissociated ethanoic acid and they are removed. Again, this maintains the pH. Buffering in the blood is based around the carbonic acid bicarbonate buffering system. If you look at the equations above, you can see that when you add acid, they react with the bicarbonate and the equilibrium moves to the left-hand side, which increases the amount of carbonic acid, which then can be reduced by increasing our breathing rate. If we add alkali, the equilibrium moves to the right-hand side because the alkali reacts with the carbonic acid. This decreases the amount of carbonic acid and it can be increased again by reducing our breathing rate. Buffer calculations. We're going to use two equations that we met in the previous video. Our pH for strong acid equation and also our Ka equation. We can combine those two equations together and we can create a new equation called the Henderson-Hasselbalch equation, which looks like this. When you're doing buffer calculations, you can use either set of equations, either the two on the top of the slide or the Henderson-Hasselbalch, and you will get the same answer in both cases. If the concentration of a salt and an acid are equal, if you look at the Henderson-Hasselbalch equation, you can see that the pH will equal the pKa because the log of 1 is 0. This is the first and easiest of the calculations. In this case, we have been given the concentration of the acid and the concentration of the conjugate base and the Ka. So if we use our Ka expression, we can find our H plus concentration and use it then, using our pH formula, we can find the pH and it works out at 5.07. If you want, you can try this calculation using the Henderson-Hasselbalch equation and you will get the same answer. In the second question, we have also been given the concentration of the acid and the sodium salt and also our Ka for the weak acid. Again, if you want to check, you can do the calculation either way and get the same answer. This third buffer calculation is slightly more difficult because we are adding the propanoic acid and the sodium propanoate together. So when we do that, our concentrations will change. So we need to have a strategy for working out this calculation. First of all, we need to find the moles of acid, we need to find the moles of salt, Then we need to find the new concentrations, and at that point we can use our Henderson-Hasselbalch equation. The next type of buffer calculation is where the salt is made in situ. If you read the question, you can see that the methanoic acid is being added to sodium hydroxide. When methanoic acid is added to sodium hydroxide, we make sodium methanoate. Therefore, the conjugate base has been made in situ. To carry out this calculation, we will first have to write out the balanced simple equation for the reaction of methanoic acid with sodium hydroxide. Then we'll need to work out our moles of acid and alkali. This will give us the moles of salt produced, and we can work out the moles of acid left. At that point, we can convert to concentrations and calculate the pH using the Henderson-Hasselbalch equation. This calculation is one where the acid is twice the volume of the alkali, and if you have a look, they are the same molarities. In this case, what you will find is that the pH equals the pKa. The next part of this topic is about titration curves. This is what a titration curve of a strong acid and strong alkali looks like. If you look, the pH begins at 1 and it ends at pH 12. If you look at the first portion of the titration curve, you can see that there is a slight increase in pH, and at 25 centimeters cubed we get a sharp rise in pH. We then have a slight increase in pH from 25 centimeters cubed of base being added to 50 centimeters cubed of base being added. The vertical region of the titration curve is very important, as this will be the region where we will be able to choose what indicator we use for our titration. Indicators are weak acids and partially dissociate in aqueous solution. What we will find is they are different colours in acidic solutions and in alkaline solutions. The indicators that we will have to study at A2 level are methyl orange and phenolphthalein. Phenolphthalein and methyl orange are the main indicators of choice. Both can be used for strong acid, strong base titrations. Methyl orange is used for weak base titrations and phenolphthalein is used for weak acid titrations. We have 4 titration curves that we are going to look at. The first is a strong acid, strong base titration curve. Again, you will see the pH starts at 1 and finishes above 12. If you look at the vertical region, it is between pH 3 and pH 10. So therefore the indicators phenolphthalein and methyl orange are both suitable in this case because the indicator changes colour in the vertical section of the curve. If we look at our strong acid weak base titration curve, you can see that the curve finishes at about pH 9. The vertical region of the curve is pH 3 to pH 8, and this is where methyl orange has its colour change, so it would be a suitable indicator for this type of titration. The next type of titration curve is a weak acid strong base. Here the vertical region is in pH 6 to 10, where phenolphthalein is a suitable indicator. We need to remember when we look at a weak acid strong base titration curve that we can have buffering occurring. Previously we have seen that a weak acid can react with sodium hydroxide or potassium hydroxide to produce a conjugate base in situ. So when we carry out this titration curve, what we will find is when we have added half our amount of alkali, we will have a situation where our concentration of salt and concentration of acid will be the same, which means the pH will equal the pKa when half the alkali has reacted with the acid. This is important because that means when we look at a weak acid strong base titration curve, if we go to where half the alkali has been added and read off the pH, we can use that value to work out the pKa. The final type of curve is the weak acid weak base titration curve, and there is no suitable indicator for this titration, we would have to use a pH meter. The final part of this topic is on salt hydrolysis. When we look at these beakers which have salt solutions, we can see that when indicator is being added, we get different colours. This indicates that these solutions have different pHs. If we look at the salt of a strong acid and a strong base, the example being sodium chloride, it dissolves in water to form a neutral solution. The salt is fully ionised, and thus the concentration of sodium ions equals the concentration of chloride ions. Since neither of these ions undergo acid-base reactions with water, no H plus or OH minus ions are generated, so the solution is neutral. If we look at the salt of a strong acid and a weak base, the example here would be ammonium chloride or ammonium nitrate. When added to water, the ammonium ions donate a proton to the water molecule. This forms a hydronium ion which is acidic, so the solution is acidic and the pH is less than 7. If we have the salt of a weak acid and a strong base, the example here being sodium ethanoate, this type of salt forms a basic solution. So when added to water, the ethanoate ions react with water, leaving hydroxide ions. The solution is alkaline with a pH above 7. If we look at the salt of a weak acid and a weak base, the example here is ammonium ethanoate. It can be either acidic or alkaline, and this depends on the dissociation of the weak acid and base. If we look at an acidic salt, for example, the salt of a strong acid and a weak alkali, we can see that the positive ion reacts with water, donating a proton and forming a hydroxonium ion, and this gives us an acidic solution. If we look at the solution of a salt of a strong acid and a strong base, for example sodium chloride, this does not happen, so the salt is neutral. However, if we look at the salt of a weak acid and a strong base, the negative ion reacts with the water, and the water donates a proton to the negative ion, leaving hydroxide ions in solution, and this gives us an alkaline solution.